And we're back. Happy Thursday. Today, we will switch gears a little bit and look at reliability. And when we study reliability, we're thinking about how uncertainty works as it pertains to systems that are comprised of a number of interacting parts. So the reading has changed. And again, as always, please make sure you're keeping up with the reading. If you wait till the last minute, you'll be working like a dog. So please make sure to start right away. So the reading by the 10th of September is in the Barron text, chapter 2, sections 2.2.2 through 2.2.3. So the reading has updated from last time, pages 15 through 20. It's not a lot of reading, but you need to make sure you're spending an hour a day at least going through and engaging with the material. Project 1 is out, and it will be due the 15th of September, so I'll be giving you an extra weekend. The 15th of September, due at the usual 11:59 and 59 seconds, so that's 1 second before midnight. Okay, so we talked about events, and we said events need a bunch of things. Something happens, an experiment or trial. You make an observation, you observe some outcome. And this last part, we spent last time talking about what we called when can I see you again, the how often something occurs. And we express that as a proportion, a percentage per centum from the Latin. And it talks about the number or proportions of times, percentage of the time, we're going to see each observation, particular observation, occur again. So we've talked about a lot of things at this juncture. We talked about sigma algebra. We've talked about set operations. We've talked about observations and looked at events. We looked at properties for certain types of events, mutually exclusive and collectively exhaustive. We looked at probabilities of complex events that you combine through set operations. We examined the definition of a probability, its axioms, and we evaluated probabilities. We talked about events and the when can I see you again. So before we jump into reliability, let's go over a couple more tools in MATLAB. And to do this, I'm going to bring back up the stick breaking construction that we had done 2 or 3 modules ago. So let's segue to that. And for the MATLAB, you might be wondering, why did I choose MATLAB? It is an environment, yes. They also have a live version, which allows you to do it through a web page, kind of like a Jupyter notebook. And it has wonderful toolboxes, and it just plain freaking works. Everything works really, really well. They have award-winning help and tutorials. So there's plenty of information, both through MathWorks as well as online, about how to use MATLAB and how to implement certain constructs. So we'll talk a little bit more about data structures and operations on the data structures. We'll look at more functions, and we'll re-examine conditionals and loops, and we'll talk about plotting as well as histograms, and we'll build upon the stick breaking code to do this. All right. So let me load MATLAB. All right. So let me bring up the stick breaking construction implementing the die rule. And in this code, we have our stick weights, 6 of them, and they're equal because this is a fair die. And we have the event names. And when I draw your attention to the stick weights, you'll notice the notation in MATLAB for it is a little bit different. Here we have the square braces and a comma-separated list of numbers, whereas for the event names, for the outcomes for the size of the die, we have strings that are comma-separated inside of these open and curly braces. And so as you know by now, the first is a vector, and the second is a cell array. A vector is an array of numbers. A cell array is an array of arbitrary objects in MATLAB. In this case, the object I list in the events cell array are strings. And so MATLAB treats them differently because MATLAB really, really shines as it comes to vector matrix operations. So you can use MATLAB to very quickly and very efficiently compute transformations on vectors and matrices, as well as higher order types of multidimensional number arrays. So suppose if I had a vector called my vector, and that vector, when you specify it, you can have it as a comma separated list, or you can even leave out the commas if you choose. So let's say I had 1, 2, 3, 4, 5. So it's a vector, my vector, that has 5 elements, 1, 2, 3, 4, 5. And so as a vector, one of the things I can do is mathematical operations on this construct. Okay, so let me clear CLC and let me recreate that vector. Now, one of the things you'll see here is I scroll up in my history window using the up arrow, and it gives me a list of all the previous commands I've done. That's a nice little MATLABism that makes things a lot easier for you. And the power, or one of the interesting or nice parts about MATLAB, is that you can test things out in the command window. And then once you convince yourself that it works in the command window by tinkering with some construct, you can then now copy and paste it and include it in your program script that you're working on. So my vector, I can take a look at the values. I can measure its size. So if I say size of my vector, I get back the number of rows and columns. So it's 1 row and 5 columns. So let me build a matrix, my matrix. And how you build a matrix, you can build a matrix 1 row at a time. And how you specify a row is using semicolons in that list of numbers. So if I say the first row has a 1, 2, 3, if I put a semicolon there, now the numbers that follow correspond to the second row. So if I said 4, 5, 6 here, and another row, let me say 7, 8, 9. Okay. Close the square brace, semicolon, for ending the statement. So now if I look at my matrix, and you'll notice here, if I just give the name of the variable, it echoes back to the screen what that matrix is. So here we have a 3 by 3 matrix, 3 rows. There's the first row, 1, 2, 3. The second row, 4, 5, 6. Third row, 7, 8, 9. Okay. So one of the things we can do, because these are multidimensional arrays of various sorts, we can also index them. And in MATLAB, indexing into arrays is 1 space, not 0 space. So if we say my vector, if you're going to index into a vector or a number array, you're going to use the parentheses. So here, when I say my vector 1, it says access this item in the first position of the my vector array. So it's a 1. If I said give me the second one, that's a 2. So with my matrix, I can do similarly. So I can say my matrix, just to remind you what it is, my matrix, give me, open close paren, let's say this first row, the second column, right? So the first row is here. The second column is this middle. That is a 2. So let's take a look at that. I could say, give me the third row, first column. Well, the third row is here, 7, 8, 9. The first column is 7, and so it's going to give me back a 7. Now, when you index into these multidimensional arrays, whether it's a vector, a matrix, or higher dimension, you can specify something called a wildcard. And Python likes to call this slices. So if I said my vector, give me the first row, well, it's only 1 row. And when I say colon, it's going to set that colon as a wildcard, and it's going to substitute all the values from 1 to the length or the measurement of that vector. So if I say my vector 1 comma colon, it's going to give me all of the first row. So the first row, first column, second column, third column, fourth column, fifth column. So it's going to give me the entire contents of that vector. Likewise, with my matrix, suppose I said give me the second row, all the columns, it's going to give me that second row. So my matrix, let me just write it again. The second row that's here, 4, 5, 6, all columns. That's the 4, the 5, the 6 for the first, second, and third columns. So if I said my matrix, the second row, wildcard, all the columns, I get back 4, 5, 6. So you can do what looks like slices in Python in MATLAB using this wildcard. And that wildcard means MATLAB substitute all the values that you can index over for that particular dimension. Okay, so now let's take our vector, my vector, and maybe I want to multiply that vector by a number, by a scalar. Now, in vector algebra, if I multiply that vector by a scalar, every position in that vector gets multiplied by that scalar. So now I can say new vector, and let's say equals, let's say 2 times my vector. When I do that, I look at new vector, and I see that each one of these components from my vector was multiplied by 2. Okay, so you have the full availability in MATLAB of vector matrix algebra, which you'll learn in linear algebra if you're in the computer science major. And so it makes it super convenient to do a lot of such operations, vector algebra, in MathWorks, and it really shines, MATLAB does, when it comes to doing vector algebra. So now, let's take a look at some functions. Now, when we did these operations for the coin toss, right, when we run this program, let me clear it, there, CLC, and let's say we save this and run, we have a number of die rolls. Okay, so we have a large number of die rolls, and what if you wanted to know this accounting, if you will, and we'll learn more about it when it comes time to talk about distributions. Let's say you rolled this die 100 times, and you want to depict what all of the die rolls were, how many ones you got, how many twos you got, threes, 4, 5, 6, and so forth. And so what you can do is compute something called a histogram. And let's clear and CLC, clear the console. One of the things I want to empower you to do is to use MATLAB help. Help histogram. It's very extensive, as well as online. It's very extensive. And if you type help in the name of a MATLAB command, it will tell you what the command is, what all the control variables for that command, what they are, as well as some examples on how to use it. And so if you were going to use histogram, well, it would be in your best interest to look up an example, copy and paste it into your command window, try it out, and then once you're convinced that it works in the way that you want it to, you then copy and paste it into your script. So let's take a look at this generation of these outcomes, the 1, 2, 3, 4, 5, 6. And so each time we have an outcome, it's this selection, and I'm going to plot a histogram that will tell me how many 1 selections I have, 2, 3, 4, 5, and 6 selections. But in order to do that, I need to save off all those selections. So what I'm going to do, I know that I roll this die, the simulation of a die using stick breaking 100 many times. So I'm going to say the selections, create a variable that's going to allow me to save them, equals, create an empty array of zeros, and it's going to be 1 by the number of rounds, right? So it's going to be 2 dimensions. It's going to be a vector since the first dimension is only 1. And I'm going to take that array, the selections, and every time I get a selection here, in addition to printing it, I'm going to say the selections, whenever you have the rth selection, 1 comma r, is equal to whatever selection is. Okay, so now I'm saving off that die roll, and the next thing I want to do when I'm done with those num rounds many rolls, in this case num rounds is 100, I want to visualize it. So I'm going to bring up a figure and I'm going to give that figure a number. Your figures can be numbered in MATLAB. That uniquely identifies them if you want to switch between one figure or another or draw things on a different figure. So I'm going to type histogram. And for histogram, let's look at the parameters it takes. Help, histogram. And it brings up the help for histogram. And histogram, if you give it a list or vector of numbers, it will divide those numbers into a number of ranges or bins, and it'll look at how many values are within the range associated with each bin. Now, the default for the number of bins for histogram is 10, but in this case, I have 6 numbers, so I want to change this default to 6 bins. Okay, so I have figure 1, and let me say number of histogram bins, num histogram bins is equal to 6, right? Because I know I have 6 outcomes. I want to measure each of the different outcomes. So now when I type histogram, I'm going to say a histogram over the selections, and I give it num histogram bins as the other parameter. That's how many bins I have. And you'll see this histogram pop up that will measure what we're after. So if I run this, I have 100 die rolls, and this is my histogram. Now, when you look at the histogram, we can certainly change the labels. The bin label is associated with that number that's right here in the middle. So this is the bin for the first outcome, the second, third, fourth, fifth, and sixth. So if we have 100 rolls, well, we have 15, 16, 17, looks like 17. We have 17 one outcomes. We have 15 two outcomes. We have 15 three outcomes, 16 four outcomes, 23 five outcomes, and we have 14 six outcomes. Okay. So when we run this, we can select number of bins through a so-called property, or we can just call it as this really stinks. All right. So when we run this, in this case, I have num bins as a so-called property, but I can also specify number of bins there on the command line. And as we had done before, we run this, and there's my die roll. And so let's experiment with this, and let's set the number of rolls to 10 rolls of the die, and let's run that. You see, this histogram gives us an accounting of how many of those rolls were each of the 6 alternatives. Now, you think that if I rolled it 6 times, that I'd get one of each, but that's not always the case. So let's test this assertion. So we roll it once, and you'll notice we have any 1s, we have 2s, we have 3s, we have 4s, but no 1s, no 5s, or no 6s. If we certainly rerun this, we notice that it changes, right? And as we increase the number of rolls, let's say increase that to 50, we see that we get more and more representation across all of the alternatives. It's not until we have a large number of rolls, let's say 200 rolls, let's try that out, we see that it gets closer and closer to them being equal. So let's end with, say, 1,000 rolls of the die and see what we get. If we run that, we see that it gets really close to one another. If we did something like 10,000 rolls, let's see what that gives us. That's a lot of rolls of the die. And so we see that it's pretty much very even, roughly the same number of rolls for each outcome. 1676, this one is 1668. So they're off only a tiny bit from one another. And so this idea of when can I see you again corresponds to the fact that the number or proportion of times certain outcomes occur, it requires the repeated trial and observation. It's never guaranteed to be the same way both times. And even for 1,000, you can see that it changes slightly from one round of 1,000 rolls of the die to the next. Okay, and so that's a little bit about histograms. Histograms are generally useful for reporting on the accounting, if you will, of various outcomes from a stochastic system. Okay, so now the other thing I want to show you is a switch statement. Let me try help, switch, and a switch statement is an alternative to doing an if else, which can get very cumbersome. So let's say we select something called my choice, and my choice is a number, and let's say it's equal to some value 5. It could also be a string, but I'm going to use fives right now. So use numbers right now. So let's say my choice is 5, and now I want to check to see what my choice is. If my choice equals 1, else if my choice equals 2, else if my choice equals 3, etc. Let me make sure. Help, else if, else if is one word, else if my choice equals 3, else, and, right? That's very cumbersome to do, and it propagates, and it doesn't look very good. So an alternative to having multiple conditionals is to use a so-called switch statement. And a switch statement is effectively a pre-implemented if, else, if, else, if, else, if. And so the syntax of a switch, you have the switch statement, and you give it the variable of interest, my choice, and it works for cell arrays, it works for strings, it works for numbers, all sorts of data types, and then inside of the switch statement, you define what are called cases. Case, and for the case, you enumerate all of the values of interest. So say case 1, case 2, that's C++, case 2, case 3, case 4, case otherwise. Okay. So now, indented underneath each case statement, that's the action that's taken should that case be true. And so it takes that variable of interest, evaluates its value, and compares it against the first value, the second value, the third value, else, that last section. So it's kind of like having an if, else if, else if, else if, else. So we would say display it is 1, for example. And let's copy that. And let's say we wanted to display it is 2. And if we get my choice is 3, display it is 3. And then if it's 4, we want to display the string it is 4. Otherwise, we want to display the string it is 5. So now I'm going to comment out this histogram because I want to show you just this switch statement, and I don't want to roll 10,000 times. I'm just going to roll once. I don't really care so much about that section right now up above. So now, let me clear the terminal, clear memory. I'm going to run this, and you'll see it's 5 right now, so it should switch should select that last statement for the otherwise clause. So let me run that. It is 5. So let me save it again. Change it to 3, save it, and let me run it. It is 3. It is 3. Let me change it. 6. This is an error. Let's say 2. Save it, and let me run it again. And so here we have the switch statement as a construct that allows us to make a much neater, more compact way programmatically, otherwise of what the if, else if, else if, else if, cascading else's would have done. Okay, so let's exit MATLAB. Plotting. So suppose we have some data, and let's just put in some values. So let's say we want to have f of x, x equals, starting at 1, increment by 0.5, go up to 100. Okay. So then we said y is equal to x times x square. Let's square that, called a function of square or power. Okay. So a to the b power. So y equals power x 2. So we're going to raise x to the 2 power or square it. And now we want to plot what it looks like. F of x equals x squared. All right, so we're going to say figure 2 to give our figure a name. And we're going to say plot x versus y. All right, so if I do that, save, I'm going to notice, let me bring that up. Here's my figure. F of x equals x squared. All right, so this is our x squared, and this is our function. So plot will give you a so-called 2D plot. Let's try execute. You'll notice, of course, is save, exit the debugger, and we show that figure. It's a spline curve. It doesn't really look very interesting because we haven't plotted enough of the rate of the domain. So if we start from, say, negative 100, minus 100, increment by 0.5, and go up to positive 100, we'll take a look at what that spline curve looks like. It's exactly what you'd imagine a spline curve is. So we can take this figure and we can turn on a grid on, and that grid on will give us some hatch marks that make it easier to see the details of this function. So now we see the grid. And so you can scroll around inside and click your mouse, and it actually tells you the different values of x and y are corresponding. So now we can say, here is our x-axis label, x label. That's our x value. We can say y label, the label for the y-axis. That's f of x, right? And we can also give this graph a title. And say y x versus y. Okay. So let's save that and take a look at the resulting graph. So if we plot that, we see our title x versus y, x value, the label here, f of x, the label on the y-axis. Okay. So this MATLAB environment gives us a lot of powerful tools that we can use to visualize graphs and to implement systems. So let's go back to our slides, get our slides. And so we're going to reserve 3D plotting. I just showed you 2D plotting, but we're going to reserve 3D plotting and some of the functions, more sophisticated things with functions for another time, closer to when, maybe on Tuesday's class meeting. All right, so let's take a look at our next section. And so the iPhone, this is the iPhone 11 in particular. It's a very popular device. Apple has certainly sold a lot of them. And what if you decided you're going to take apart your device? Now, certainly, don't go saying, oh, well, Dr. Holmes told me to take apart my iPhone. No, Dr. Holmes is not telling you to take apart your iPhone. I'm just saying, what if? So do not take apart your iPhone. It will void the warranty, right? Don't do that. But if someone were to take apart the iPhone, well, this is taking off the top cover. You'll notice a lot of the real estate inside your iPhone is devoted to battery, right? And so you wonder, why is that? Well, that's because this iPhone, this relatively small device, needs to send a lot of current to the antenna to get signal information data from the phone to the cell tower, which could be several miles away, and vice versa, cell tower back to the iPhone. So if you take off the top cover carefully, you see a bunch of components. You see the camera, you see the circuit board, you see all sorts of electronic subsystems. And well, there's the camera in the back, stereo camera, and there are all the parts involved in the iPhone, right? And so there are two components in particular that I want to draw your attention to. These components are, let me set my pen color and set to blue and grab my digital pen. We have the main communication board. So this is the communication board. And I don't know why I'm popping up information like that. That's the communication board. Circuitry. And this is, if I recall, it's the app board, circuit board. Okay. And certainly this is the camera. On the other side here, underside here, attached or inside here, that is the back of the LCD screen or the Retina display. And you see the ribbon cables. You see the ribbon cables. For display. So this is like your monitor cable, but it's only the cables for the device itself. And so, of course, we see the battery down here. Here's our battery and battery. This is Google's image search here, tagging these different images. So we see the battery. We see all sorts of I/O components. We see some chips and other devices. So when we look at this diagram here, you'll notice that very few of these components are actually made by Apple. Well, this is the app's PC board, personal computer board. We have the A13 chip. Well, that's made by Apple, right? That's made by Apple. We have some other components made by Apple here, the audio codec for coding and decoding audio files. But the majority of components are made by other corporations. Intel, USI, National Semiconductor, flash driver, Cirrus Logic, the audio amplifier, all sorts of companies make it, and very few parts are actually made by Apple. Now, what makes an iPhone is the integration and the software, and not so much the components. Well, certainly the chipset plays a pretty important role in that. But very few parts are actually made by Apple. Apple integrates these parts into a nice system that does a lot of things for you. And so this is the inside of an iPhone 11. And again, I stress, do not take apart your iPhone, right? It will void your warranty. Okay. And so you have a lot of interacting parts, but when one system fails on your iPhone, so let's say there's something going wrong with the Skyworks GPS, what is the consequence of that failure? Well, what you need is to know how these parts operate and what are the interconnections between these parts. What depends on what depends on what. And so a system consists of components, and these components interact, and sometimes they fail. And so one of the questions you might ask in terms of uncertainty, can you use the failure rate for each component and how they interact to determine the behavior of an entire system? Now, there's a whole field in doing this reliability analysis, and it's very, very important. And what this reliability analysis module in the course is about is how you think about constructing eventually what will be simulations of complex systems that have many interacting components. How do you simulate this? Now, we've been talking about a die roll, and we've talked about a coin flip, but suppose you have a system, each consisting of components like your iPhone, and each of these components can either run or fail with a certain probability. Now, of course, given that probability, it's the interactions between them. So you compose a more complex system where one component depends on the output of another component, depends on the output of another component. How do you take the entire system and now analyze the uncertainty that the system will run or fail, the system's behavior? So this is the subject of reliability, and the example in the book, this is from the reading, is a redundant disk array. So here we have a redundant disk array, and in a redundant disk, you use redundancy or multiple disks as a way to try to increase reliability. So if one disk fails, another disk takes over from the failing disk, and the system as a whole keeps running. So in the book, the specification they give you is that you have a storage array, and there's a 1% probability per centum, or 1% probability that a given hard drive is going to crash. Therefore, in order to increase reliability, not only do you have that hard drive in your storage array, you also have two backups. So that's one primary drive and two backups, or a total of 3 disks. But each of the backups has a different probability of crashing. Each of those backups has a 2% probability of crashing. And so the disk components are independent of one another. The running or failing of the primary drive does not impact the running or failure of the first backup, and does not impact the running or failure of the second backup, and the backups don't impact one another in terms of the running or failure. So each one of these components are independent of one another. And so the question then, information is lost only when all 3 of these devices, the primary hard drive, the first backup, and the second backup, crash. And so one question you might ask, as a system, what is the probability that information, when you write it to this disk array, that it's actually going to be saved and it's not going to crash? Okay, so that's a reasonable question you might want to ask. What is the reliability? Well, what is the probability that when you go to write information, you go to save it, that it actually is saved? So going back to what we've discussed before, associated with a stochastic system, we have 3 components. What is occurring or happening? That's the experiment. What do you observe? And when can I see you again? And so let's go through these in curves. What is occurring? Well, boom, your disk breaks. Something happens. That's the experiment that happens. You turn on your disk, or you go to use it. Does it write? Does it operate correctly? Or does it fail? Okay. Well, what do you observe? Let's think about this. So let's make some definitions here. We're going to use sets to describe these events that can occur. So let's talk about H. We're going to say let H be the set that describes the event for the hard drive crashing, and let B1 be the event for the first backup crashing, and let's define B2 to be the event corresponding to the second backup crashing. Okay, so that's what we're going to observe. Well, we're not quite done yet, because if you have a hard drive that can crash, you can also have a hard drive that can run. And so let's kind of clean this up a little bit, manipulate this, and we'll talk about all of the observations, because crashing isn't the only observation. It can also run. So by our definition before, H is the crash event, and rather than using words, let's use more compact notation, because this compact notation kind of makes it easier for us to talk about the system. So instead of using the words hard drive crash, first backup crash, second backup crash, we're going to be more compact. So H is this event, C sub H, which is the event for hard drive crashing. B1, first backup, is C sub 1, which is first backup crashing. And likewise, C2, little c2, with a subscript 2, is the event corresponding to the second backup crashing. So if we know it crashes and we know it can run, we have not yet completely defined sample space omega for the primary disk, for the first backup, or for the second backup, until we also represent the opposite of crashing, which is to run. So our omega disk, therefore, will be the union between the event of the hard drive crashing, that's H, and the complement of H. So we have omega disk is H union, not H. Likewise, for the first backup and second backup, we do similarly. we have omega backup, the sample space corresponding to the first backup running. We have B1, the event for crashing, and not B1, which is the event for not crashing or running. And we do the same thing for the second backup. Okay, so now this notation, if we look at it, it's kind of cumbersome. It's kind of a little bit still too hard to deal with. So let's further clean this up. Okay, so we're going to say CH is the hard drive crashing, the main drive. C1 is the first backup crashing, and C2 is a second backup crashing. So let's also talk about the run state and use variables to do that as well. So RH is going to mean the hard drive runs, which is the same as not crashing. CR1 is going to mean the first backup runs, which is the same as not crashing. And R2 is going to correspond to the second backup running. So if we go over here on the side, let me direct your attention over here. So now what was before for omega disk drive, the run union with the not run, we now have omega disk is the crash event for the hard drive union with the run event. We do the same thing for backup 1 and 2. So now we have omega backup 1 is C1, comma R1, and omega backup 2 is C2, comma R2. And so this notation is a lot more compact. It allows us more easily to look at what's going on rather than just saying H and not H, B1 and not B1. Okay, so we've cleaned things up a little bit, and let's rewrite our sample space omega for omega disk, omega backup 1, and omega backup 2. So in the problem statement, we said that the probability that your hard drive crashes is 1%. As a percentage, a proportion per centum, it's 0.01. The probability that the first backup crashes is 2%. Per centum, it's 0.02. And likewise, the probability that the second backup crashes from the original problem statement is 2% as well, per centum or percent is 0.02. So that being the case, now we can fill in what the run probabilities are. Okay, well, what are those run probabilities? And more importantly, what rule do you apply? Well, that rule you apply, we talked about that. It's called the rule of total probability. And what does total probability say? It says the probability of my sample space omega is equal to 1. So we know that our sample space omega in either case consists of two things. Probability of omega is the same as the probability in the case of the disk. Probability of omega disk, that's equal to 1. That's equal to the probability of the union between the crash state of the disk union with the run state of the hard drive. Okay, so if we do that, well, we know that the intersection between the crash and the run is empty, right? They are disjoint. So if we took the intersection between CH and RH, that's equal to the empty set. So that means they're pairwise disjoint. If they're pairwise disjoint, that means we can add these together. So let's write up here the probability of the crash state for the hard drive, curly brace, union with the run state for the hard drive is equal to the probability of the crash state plus the probability of the run state for the hard drive. Now, we just said this sum is equal to 1 by total probability. So if that's the case, well, we know what probability of CH is. We know from the problem definition that's 0.01. So this gives us 0.01 plus the probability of the run state for the hard drive is equal to 1. Subtract 0.01 for both sides, and we get the probability of the run state for the hard drive is equal to 1 minus 0.01, which is 0.99, which is 99.9%. Okay. Oh, 99.9%, I should say. 99.9%. And so that is, yeah, 99%. It is 99%. I had it right the first time. 99%. Okay. And so that is the probability that the hard drive will run. And we make use of total probability to do that. So if we do similarly for the first backup and the second backup, that is just 99% for the hard drive. We have 98% for the first backup and 98% likewise for the second backup. And so the important thing here is to recognize the rules or the properties you employ when you're trying to do these computations. So now we have the probabilities by law of total probability for the run and the crash for the hard drive, the run and the crash for the first backup, the run and the crash probability for the second backup. Okay, so now the question then is, what is the probability that information will be saved? Okay. Likewise, we can look at the probability of information being lost. And so for information to be lost, what has to happen? We lose information only when all the three devices crash. The primary hard drive crashes, the first backup crashes, and also the second backup crashes. So that means each of them, CH, C1, and C2, have to be true in order for this system, this redundant system, to fail. Okay, so information is only lost when all three devices crash, and we know that the operation of these devices is independent. Likewise, the running of these are independent. And why is that? Well, the status of one does not impact the status of another, right? That's given to you that they're independent. So if we were to compute the information lost condition, that means all three have to fail. That means you have the probability of the hard drive failing here, this first part of the expression, CH, hard drive failing, C1, backup 1 failing, and at the same time, the second backup fails. And so for all three to crash, that means hard drive crashes, and at the same time, first backup crashes, and at the same time, second backup crashes. So because they're independent, we said in an earlier module that if you have independent events, that the probability of the intersection, the ANDing, if you want to call it that, is equal to the product of the individual probabilities. So that's the product of probability of CH times probability of C1 times the probability of C2. Okay. So if we want to know the probability that information is lost, we can do it in this fashion. We multiply the crash rates for each of them together, because all three devices have to crash and they're independent from one another. They have to crash in order for the system to fail. And so we know that's for the information being lost. So if we were to ask, or go back to the question, what is the probability that information is saved? Well, if we have our system, well, it has two states for this system. The system can either run or it can fail. So on the outside, we have our disk system. It consists of the hard drive. It consists of the first backup. It consists of the second backup. And we know they operate independently. So if this system can either run or fail, we just computed the probability of failure, right? That probability of failure is just the product of the three crash rates. Okay, the crash probabilities. So if we want to know the probability of information saved or not lost, well, lost is this probability, fail. Run is just this probability. We have two alternatives. So by law of total probability, it's just 1 minus the probability of failure of the entire system. Okay, so that being the case, if we want to know the probability that when you save information to this redundant disk device, that it's actually going to be saved, that means that probability is saved by law of total probability is 1 minus the probability of loss. And we know what this probability of loss is by multiplying those three crash rates together. Okay, so let's take a look at this. Probability that information is lost is this crash, backup 1 crash, and backup 2 crash. We know that it's the product of the 3 crash rate probabilities, and the saved rate is 1 minus loss. So let's plug in 1 minus loss. We take the 1 minus the probability of crash, CH, times the probability C1, probability C2. We substitute in for what those crash rates are. So we substitute a 0.01 for probability of CH, a 0.02 for probability C1, 0.02 for probability of C2, which is the crash rate for backup 2. All right, so we do that, and we multiply these 3 terms together, and we take that product and we subtract it from 1. And this gives us 0.999996 is the probability that the system is going to save data. Now, if we were to think about it as a crash rate, that would mean it's going to crash 4 times in every 1 million saves, right? And we get that figure by just looking at the proportion if we have that 4 written here, 4 out of a million as a decimal. Okay, so that's how we would compute this. And one of the key takeaways from this exercise or this example, and it's in the book, the key takeaway is you'll notice we wanted to compute the probability that information is saved, right? And we did that by subtracting 1 from the probability that information is lost and making use of the law of total probability. Now, of course, when you're solving a practical problem, you want to consider both the positive logic as well as the negative logic, the dual. Is it easier to compute one probability versus the other? Now, when you're solving a problem, if you find that something is very difficult, you want to try looking at 1 minus the dual, as it were, because sometimes that's a lot easier to solve. Okay, so one of the things we can have is this dependence on the output of another component when you're operating in a system. So take, for example, your antenna in the iPhone 11. The antenna in the iPhone 11, it takes as input the output of your battery. So regardless of what your antenna is doing, if the battery output fails, the antenna is going to fail, even though they operate independently. Well, in that case, they don't really. The battery operates independently, but the antenna does not operate independently. And the reason for that is that without the output of the battery, that antenna can't function. And so one of the things we need to be able to describe when we have a set of parts interacting in a system, if we want to analyze its reliability, the probability that it's going to run or crash, or the probability of certain types of behaviors, we need to be able to encode that type of dependence, like how the antenna depends on the output of the battery. So we start out and we perform an experiment, and we get some event, and that event depends on the experiment. An event occurs, and it has many possibilities. Something occurs some percentage of the time, and we make an observation. And so here, I'm going to introduce a kind of stock flow diagram, and this is going to be used graphically to depict the dependence of one component on another component. And so here, the arrow direction denotes this idea of depends on. And so in this particular event, it depends on the output of another event, and you get some observation that depends on that particular outcome that occurred. And so we can use these stock flow diagrams to effectively analyze the interdependence of different parts in a subsystem, each of which is uncertain, and incorporate them to build a model, if you will, or description of the success or failure or behavior or operation of a complex system comprised of a set of interacting components. Okay, and so one of the relationships that we have, and we'll look at this from the perspective of our redundant disk that we just examined. Think about the question that it's asking you. So you have a start, and you'll notice here these edges. I can trace paths from left to right. There's a path along the top, there's a path along the center, and there's a path along the bottom. Now, this particular assembly is called a parallel path, a parallel circuit. And parallel, you'll notice here that for each one of these disks, the hard disk, the first backup, the second backup, the output of one disk does not depend on the input of another disk. They are in parallel. And so how we organize this idea of the output of one component does not depend on the input of one component does not depend on the output of another component, we can encode that as a set of parallel paths or so-called parallel circuit for our stock flow diagram. So we have the system that runs or crashes, and we notice that each one of these components, they can run, and the output or observable, they could crash or it could be a run. But the crash output of the hard drive does not impact the run or crash of the first backup and does not impact the run or crash of the second backup. They all operate without influencing one another. And so this parallel relationship encodes this idea of not being influenced by someone else's outputs. Okay. And so a stock flow diagram is something from a larger body of work or discipline. It's employed in a discipline's operations research. And you'll notice that the events in omega disk for our hard drive, omega backup 1 and omega backup 2, do not depend on one another. If you get a run or a crash output from the hard drive, it does not impact at all what's going to happen in the first backup or the second backup. And this is captured by these parallel paths as we go from start to the observation of the event from left to right. And this idea of not depending on another, no interconnection, is captured by these parallel paths in the stock flow diagram. Okay, and so the question that was asked, what is the probability that information is saved given those numbers where the hard drive crash rate was 1% and the backup 1 and backup 2 were both had a crash rate of 2%? So essentially what we want to know, if information is saved, we want to know what's the probability that the hard drive runs or backup 1 runs or backup 2 runs. So we're talking about a logical expression here describing the condition where there is no dependence. And this is encoded by the parallel circuit. So we take these unions and we don't know a priori if these particular systems are independent or not. And so we covered this idea of a three-way union before. And so we're just going to expand that definition. The probability of the union combination of things that you don't know are overlapping or not is the sum of the individual probabilities minus the probabilities of the two-way intersections. So here we have the hard drive running intersect with the first backup, hard drive with the second backup, first backup with the second backup. So we have minus the two-way intersections, those probabilities, and then plus the three-way intersection to add back that three-way intersection portion that was removed when we subtract these three two-way intersections. And so we take this expression and then we use the fact that these individual components are independent to actually plug in these values. Now, if you look at this expression, there's a lot to compute, right? We're computing three additions of probabilities. We're computing subtracting the computation of three computations of two-way intersections, and then we're adding a three-way intersection. There are a lot of terms there and a lot of opportunities to make a mistake. But you'll notice when we first solved this problem, we took advantage of the easier problem by looking at the probability that information is lost and just using total probability and subtracting it from 1. It was much, much easier to do. But I'm going to prove to you it's the same result whether we do it this long way, where there are more opportunities to make a mistake, or we do it the short way. And what this illustrates really is just that if you're solving a problem in reliability, trying to find an expression that describes an entire system's behavior, that if you find you have a very complex expression to solve, you might want to simplify it and think of the negative logic. So if you think about run is 1 minus crash, and maybe that crash state for the entire system is a lot easier to solve for. Okay, so let's do it the long way and show that this is the same expression. So we plug in the run rate. So we have the probability of hard drive running union the first backup running union with the second backup running. So filling in for the probabilities of the individual events, That's 99% run rate for the hard drive, and we calculated that before, plus 98%, plus 98%. Okay, so now we subtract out the two-way intersections. Now, these things running are independent, so when we have disjoint events, we compute the probability of the intersection as being the product of the individual probabilities. So here we have the product of the hard drive run with the first backup run. So that's 99 times 98. So here we have hard drive run, second backup, 99 times 98%, and then we have the first backup and the second backup. We multiply those probabilities together, 0.98 times 0.98. So now for the three-way intersection, again, these three components run independently and crash independently, so they're disjoint, and therefore the probability of the intersection is the product of the individual probabilities. So we have the hard drive multiplied with the probability of the run rate for the first backup multiplied with the probability of the run rate for the second backup, and we get addition of 90.99 times 0.98 times 0.98. Okay, so if we do this computation, we end up that the probability of the hard drive run union with the first backup run union with the second backup run is equal to 0.999996, which is the same result that we got before. Okay, and so you can either do it the hard way or you can do it the easy way. And it's a lot easier to compute this as just probability of save, meaning all three hard drives, at least one runs, hard drive run union, first backup run union, second backup run. It's a lot easier to solve it as using total probability, 1 minus the probability that information is lost. Okay, so let's talk about this other case where you do have this dependence. The output of one component influences the input of the next component. In this case, you can assume that the components operate independently, but there's an issue. The output of one impacts the input of another. And an example for this is, suppose a hard disk has two drives, a disk array. The first drive stores the table of contents, and the second drive stores the actual data itself. So let me draw a figure describing what that might look like. So we have our system here, and you're going to store information. You have the first disk, the hard drive, and that hard drive has your file table, your table of contents. And you have a second hard drive, your backup, let's say, we'll call it B, but it's not really a backup. And every piece of information in the hard drive tells you where on the backup you're going to find the data for that file. Now, in that particular case, the disks themselves operate independently, but because the data disk depends on the table of contents, the file table, there's a dependence there, and the operation of the data disk is going to depend on the operation of the file table disk. So that means the crash of the first one is going to result in the second one not operating correctly. And likewise, if the second one crashes, well, it doesn't matter what that table says because you won't access the data. And so this is an example of so-called sequential dependence. And in the stock flow diagram, we depict it as what we call a sequential or a series circuit. So as we go from left to right, we start, you run your hard drive, it either runs or crashes, you observe that event, and then you have your backup disk, and the crash of that output observation of that table of contents impacts that second disk where the data table exists, right? And that data table, well, let's assume that it runs with the table of contents runs or the file table runs correctly. If that data containing disk, that data disk crashes, well, you're going to get an output of a crash. If this first one crashes, well, it doesn't matter whether the second one runs or not. Because the file table crashed, you're not going to access the data. And so this is an example of so-called sequential dependence. One depends on the other. And that's more similar with the iPhone example to what happens to your antenna if the battery fails. Because without the battery, you're not going to get current to power the antenna, regardless of whether the antenna can generate electromagnetic signals or not. Okay, so If you lose the table of contents, the data on backup one, that this disk we're calling backup one, is useless. So in that particular case, the probability of saving information means that the primary hard drive with the table of contents runs, and at the same time, that data disk we're calling backup one is going to run as well. So that's the condition you need. Both of them must function in order to save information. And that's what this logical expression means. So if we said that the physical disks operate independently, the probability of the intersection between two disjoint variables, which means independence, is the product of the two variables' probabilities. So this is the probability that information is saved. And so if we do that, we have an expression for how you determine what the probability is for the entire system, where that system consists of a sequential interaction between the two independent components. And so here we have our disk array, and we know that we have two components, the table of contents or the file table, and that influences the data storage. If we want to know, if we already know the crash rate or run rate of each one of these, so this is R1, RH I mean, and this is R1, what we want to know is what is the probability of running for the entire disk array. And because we have this sequential circuit, well, what is that probability that the array runs or saves data? Runs. That's nothing more than just the probability that the first component runs, RH, multiplied by the probability that the second component runs, R1. So why do we do this? Because we take this expression, and now we don't care about the internals of the disk array. We just treat that disk array as having a probability that is just that product instead of looking at the individual components. So that's why we do this. So the sequential dependence and the parallel dependence are just methodologies for how you combine the known crash and run rates for the individual components based on their dependence on one another. How do you combine them into an expression where you can just forget about what is inside of that device and treat it as a black box that's associated with a particular expression for the crash rate or the run rate? Okay, so you can also have a so-called mixed circuit, and in this particular case, we combine serial and parallel connections. So you notice as you go from left to right, here's the input, the start, and here is the output of the entire system. So this is a whole system. We know what the components are, and we know what the dependents are. So here, component B has a certain run and crash rate. A does, C, D, and E do as well. And so now what do? We want to effectively find equivalent expressions for each of the subsystems, combine them in some way in serial or parallel combinations, and then find equivalent expressions, and then keep doing that until we get a single expression. So the first thing we're going to do, okay, well, we know that A and B have that serial relationship. So we're going to treat this A followed by B in serial connection as a single component. So you're going to find an expression for that as a serial component. And in doing so, you're going to remove the A and the B and replace it with a single box that encodes the equivalent probability for this assembly, this serial sub-assembly. Likewise, if we look here and we look here, we see that D and E are in a parallel connection. Well, we know how to treat parallel connections. We treat that as a single subsystem, and we compute the equivalent expression for two components, D and E, each of which has an individual crash rate and run rate. And once we get that equivalent expression, we then replace that D in parallel with E with that equivalent probability and treat it as one component. So if we do that, we call that equivalent component for the A in serial or series with B as a component F, a new one we introduce, and we treat this as component G. And if we do that, we get the following equivalent circuit. We have the start, we have F, which has the behavior of this serial connection between A and B. We have C, and we have this G, and you notice this equivalent component is in serial with C, but this G, we came up with the expression, the equivalent expression for D in parallel with E. So we take this C and G now, and we can notice that C is in serial with G, and we combine those two, the expression for C's reliability, running or failing, with now the new expression we computed from before for G. So we do that, and we can now erase these two and replace it with what we'll call H, and now we're left with F in parallel with H. We take that equivalent expression, we combine what we know for parallel circuits, those two expressions, and now we can get rid of that. And what if we call this equivalent expression I? So now the reliability of this original circuit is just an input, and we have I, and the probability of run or fail or crash is just whatever that expression is for I. And each step along the way, we're reducing our circuit by observing the dependence of one component for another with another, and combining them using what we know from the rules that we've covered thus far. Okay. So I'm going to end there. This is all I had. And with that, we will pick back up on Tuesday. Have a great weekend. And as always, stay healthy and stay safe.